recuperate some time. So, so this paper is a cooperation with some colleagues from University of Limoges in France. They are specialists in ceramics, and we try to determine the fracture properties for some composite materials doped with some ceramic kaolin particles. So basically, we have a materials presentation, the process of elaboration. We use the Brazilian disc specimens in order to do mixed mode fracture toughness. I will present a little bit the experiments and the evaluation of the fracture criteria. So basically, nowadays, due to circular economy and we want to decrease the volume of plastic materials, so and to be environmentally friendly. So in polymeric materials, there are added different types of particles. In our case, kaolin. The main application of this are electric insulators, which are used for transporting the energy. So we have a polymer resin, which is an unsaturated polymer resin, which has good electrical insulation properties, low viscosity, and excellent adhesion and low shrinkage. And these are mixed with ceramic materials like kaolin, in this case with some particles having an average diameter of 92 micrometers. So the process consists in mixing the two components with some methyl ketone peroxide and ethanol, then pouring in an aluminum cylindrical mold, which was placed on a vibrating table, then photopolymerization, which was occurred at room temperature, and what we consider the full photopolymerization after 3 days, and then preparation of the specimen, cutting the specimen, the Brazilian disc specimen in a CNC milling, then with a water jet cutting the notch. So we use classical Brazilian disc solution, where we have two let's say main parameter, which is the crack angle and the crack length. Our disc has a diameter of 24 millimeters, and the crack length was 11 millimeters. We perform, prior to do the test, some finite element analysis to determine the non-dimensional stress intensity factor for different angles between applying the load and the crack orientation. And we found that at around 23.1 degrees, we have pure mode 2. And between pure mode 1 and pure mode 2, we choose several crack orientations in order to do the test in mixed mode. Our tests were performed at room temperature in our testing machine, considering the two extreme 0 degrees and 23 degrees for mode 1, mode 2, and other 3 crack orientation, 10 degrees, 15 and 20 degrees. We consider 2 proportion of fillers, so 0 without fillers, 7.5% volume fraction and 15% volume fraction kaolin fillers. And we use the classical fracture criteria of Erdogan 6, maximum tensile stress, equivalent stress intensity factor of Ricard, and strain energy density criteria of SIG. And we try to express our data side by side with these theoretical predictions of the fracture. We got quite good agreement with the Ricard criterion. I have to point out here that the Ricard criterion is the only one which takes into account also the fracture toughness in mode 2 through this, let's say, alpha parameter, which is the ratio between mode 1 and mode 2 fracture toughness. And it looks that trigger the curve in order to have good predictions, at least at the end of the interval, pure mode 1 and pure mode 2. 0% filler, 75% filler, and finally 15% filler. Here, data are more scattered, but what we observed in the previous test done in tensile, in Limoges, they also observed that at 15% filler and more, 20%, the results became worse. Probably the adhesion and the incorporating of the filler is not anymore uniform, and the results are not so good. What we can see here, the mode 1 and mode 2 fracture toughness increase with the increasing the filler proportion up to 15%. But on the other side, the ratio between mode 2 and mode 1 fracture toughness is decreasing from around 1.5 to 1.1. I mentioned we observe similar tendency for the static tensile test and for some sharpening.